Hello, my name is Ryan Pearman. I'm the Director of Modeling at D2S, and welcome to the second installment of my Mask Modeling Fine Line webinar. If you missed the first installment, I recommend going back and reviewing it again. It should be archived on this site. Now, today, the topic we're going to talk about, which is often taken by granted by many process engineers, is to understand how the electrons, which are deposited from the eBeam illumination tool, interact with materials in the resist stack. Now, the mask stack can be very complicated, from an EUV mask where one would have a resist on top of an anti-reflective coating, on top of a absorber, on top of a molybdenum silicide multi-layer, or it can be relatively simple with a binary mask where you have a resist on chrome on glass. But in all cases, the resist is the important material. It is the thing that transfers the pattern to the reticle and further etch steps. So the question is, what happens to the resist both during and after the eBeam illumination step? So the answer lies in the composition of the resist itself. Even as a chemist, my mental image of the resist still resembles that of a spaghetti with some mystery meatballs inside. You have long, twisty polymer chains with various reactive sites, as well as other groups sprinkled within the matrix. Instant electrons will react with these individual groups in some way, and by doing so, create the changes we want in the resist. So last time, we talked about the eBeam writer step, and in particular, the details of how energy scatters into the mask reticle stack. A shaped VSB electron beam is demagnified into the mask stack, and then the electrons subsequently scatter over a couple of different length scales, 10 nanometers and 10 microns. The important message to remember is that both regimes are from the high-energy electrons elastically scattering with the various molecules. This results in transmitting mostly vibrational energy, or heat, to the resist. However, every so often, and more often as the electrons slow down, the electrons are captured by a resist molecule and will eject a secondary electron. Now, it is the secondary electrons, which typically have low energies, that are most well suited to be captured by these molecules in the resist. They then transfer their electronic energy and create the chemical changes we are interested in. So to start with, we'll go back a little bit in history and talk about the simplest photoresist possible, PMMA. Now, PMMA is really nothing but a long, simple hydrocarbon polymer chain that's insoluble to an aqueous solution. So the secondary electron capture events will result essentially in a breaking of carbon-carbon bonds in these long chains. Such reactions then, electron by electron, will create shorter and shorter polymers, and as a result, they will be increasingly more soluble to the aqueous solution. So in this picture, we represent the bond scission from R to R star as they absorb the electronic energy during the electron beam right itself. Now, other forms of conventional resist function not on carbon-carbon scission, but rather on changes in functional group side chains. Here, secondary electrons can excite an electronic state into a dissociative state, which can then change the polarity of the polymer units, increasing the solubility in the aqueous solution. Now, in both cases, these low-energy electrons activate as a solubility switch, which allows further resist processing, in other words, development, to remove areas of exposed resist. What we show here is a typical resist image where the R star in yellow is present where the resist no longer is, and the remainder of the purple is the unreacted resist. So let's step forward in time where higher energies in the eBeam tools, as well as right time considerations for the entire mask process, becomes important. Now, one of the main reasons why a 50 keV eBeam tool was instituted was to reduce the forward scattering and therefore increase the ultimate resolution of the eBeam writing step. Now, unfortunately, conventional resists are relatively slow, and the high energy of the 50 keV eBeam made those resists even slower still, mainly because the secondary electron scattering cross-section goes down as the eBeam voltage goes up. So what the mask process engineers had to do was to take a trick out of the wafer fab process playbook and introduce something called a chemically amplified resist. Such a resist is much more complicated. In addition to the polymer reaction sites, other additional materials are also included in the photoresist. the most important of them being the PAG, or the photoacid generator. These are designed to significantly reduce the number of electrons required to print a major feature. We'll see how that is shortly. Some other formulations also include a base to further enhance the resolution. Now, importantly, what happens here is the electrons no longer directly react with the reactive species in the polymer backbone itself. Rather, the electrons go to breaking apart the PAG into a free acid, which at the right time does really very little to generate this resist. Further processing step, called a post-bake, then is necessary, during which some really neat chemistry begins to happen. First, and most importantly, is that this acid catalyzes a reaction with various groups in the photoresist, which simply means the presence of the acid is required to go from R to R star, but the acid itself is not used up in the process. What that means is a single acid generation event can be used to create many solubility switch events, effectively raising the resist sensitivity. Now next, the acid itself is small enough such that it can diffuse over tens of nanometers inside the resist during the post-bake. This diffusion is effectively a blur, which will then sit on top of the forward and secondary electron scattering. Given its length scales, it turns out that this diffusion itself represents the majority of single Gaussian forward scattering mask models that are in use today. Now, this could be a resolution limiter, and certainly it is compared to conventional resists, but it is more than made up for in the reduction of the blur possible by moving to a 50 keV eBeam tool. There's one additional advantage to this blur, in that it tends to average out individual electron shot noise, as well as material non-uniformities inside the resist, which will then significantly reduce line edge roughness in the process. Now lastly, we can mitigate this blur somewhat by the addition of bases into the resist. Typically these have much slower diffusion speeds, so it serves to enhance the resolution by limiting the extent to which acid can diffuse away in the material. Bases will quench the acid away from highly exposed regions, significantly reducing the Gaussian tail of the acid diffusion while maintaining the line edge roughness advantage. Now, what I describe here is but a subset, but a very important one, of all the possible things that can happen in a chemically amplified resist. But compared to conventional resist, there's clearly a lot more going on. You have diffusion of acid. You have acid and resistor reaction. You have acid and base quenching. We have to keep track of all of these things in addition to where the electrons go to successfully model the mask process. So in the past couple of slides, we've talked briefly in passing about the concept of developing the resist away. Let's talk about how that actually works. So after the post-bake, an aqueous basic solvent is introduced in either a puddle or other form to the resist surface. Now, because the resist is nonpolar and the solution is polar, the unreacted resist is relatively unaffected by the presence of this solution. Think oil and water is a good analogy. It's really only the very small oil particles that emulsify into the water. However, those portions of the resist that have been switched, these locations have an increasing affinity for dissolution, such that the rate at which the resist is dissolved into the developer is dependent upon the overall percentage of the resist that has been reacted. However, this dependence on the overall percentage of resist reaction is not linear. In fact, it's almost step function-like, where there can be thought of as a threshold reaction percentage over which the resist is completely soluble and under which the resist is completely insoluble. So this threshold of solubility then gives rise then to a threshold of acid concentration, which then gives rise to a threshold of eBeam exposure, which gives rise to the concept of a constant threshold model that we use in mask modeling today. Unfortunately, this idea of a step function switch to solubility is not quite borne out in reality. In fact, the rate curve is somewhat more broad, but that gives rise to some other interesting physics. Now, the dissolution rate is usually quite rapid vertically in exposed areas of the resist, as one typically sees a fast reaction rate amongst the resist thickness. Now, because of the acid and other blurs involved, there are non-negligible transitions between fully unexposed as well as fully exposed regions, as indicated in this particular region on the slide. Because of this, development will proceed, but it proceeds quite a bit more slowly in these regions, and you'll find that development after going down will move laterally relatively slowly, as material is attacked from both the top as well as the side. Now, as an aside, this lateral rate here becomes faster as the dose margin decreases due to a larger partially soluble length scale and the larger transition in the unexposed regions. Now, this can seemingly give rise to sublinear behavior in line linearity for small lines. What's also interesting to note is that a smaller dose slope results in more variance in the resist composition over a larger length scale, directly giving rise to increased LER. And you'll see this for any low contrast site. That being said, there's another key nonlinearity to talk about, which serves to seemingly counterintuitively slow the dissolution rate down as the resist exposure gets larger. We call that microloading. Consider what happens if we encounter a large area of reacted resist. All the resist will, in principle, develop very quickly into solution. But what I failed to mention is that the solvent-resist interface behaves very similarly to a gel and has relatively high viscosity compared to the bulk solution. Large exposures then result in a significant percentage of resist in this local gel, effectively blocking further resist from dissolving. This impact will be seen by slowing down the slowest dissolution rates first, which is that of the lateral resist development. That results in an iso versus dense region print bias observable on reticle. So that's it then. We've covered a lot of physics and chemistry at a very basic level in a very short amount of time, but we do have all the pieces we need to successfully model the features you would see in the resist on a reticle. You start with a VSB shape. You project it to the mask stack by blurring it due to the Coulomb blur. You add another blur to deal with electron scattering. You then go to the resist and do some resist magic to convert those electrons into acids and then into reacted sites. From reacted sites, then you can go to a development rate, go down here and do some dissolution dynamics and calculate resist profiles. Simple, huh? No. Next time, we'll actually go and talk about the missing piece, which is what happens when we actually apply some etch to this resist stack. And then afterwards, we'll actually put some math to what we just talked about. See you next time.